Okay, good morning, afternoon, evening, whatever case might be. Today I've got a little bit of information to give before I do the video on vectors, and the information is this, that I noticed in office hours that some of you do not have the second edition of our book, but are using the first edition. Most of the text is the same, but the problems are quite different. So this is what the second edition looks like. The first edition has a lighter blue cover. So that's the one you want, the second edition, and you'll want that. Now, there's another issue that if you have picked up kind of a rogue Facebook PDF of this book, there's one out there, but check the problems to make sure that the problems on your PDF are legible. So I know that for some of you, the problem section, the text is fine, other than perhaps some missing subscripts, but the problems are almost unreadable. And I will be assigning a lot of problems out of the book. That's what I'm looking for, the library getting us permission to use PDFs of at least the problem sets. I haven't heard back from them yet, but I should hear back even this afternoon about that. So make sure that your problem sets look good. If they don't, maybe you can have somebody else in your group make you a video of the problem sets that we're having for today, and by the end of the week we should have this settled. So anyway, today I wanted to talk about vectors in Rn. And there are several things to talk about here. So for the most part, I'll be talking about R2 or R3, but it works the same in all of the dimensions. For us, for example, if we're in R2, the kind of points that we have are points like 1, 2. And we plot that point in the x1, x2 plane, 2 dimensions, 1 over 2 up. There's the point 1, 2. Now, a vector is not so much telling you a location, but rather telling you how to get from one location to the other. So that's the difference. In many instances, different notation would be used for the vector 1, 2. But for us in our book, we use the same notation for point as we do for vector. So if I'm going to interpret 1, 2 as a vector and not just a point, what vector is it? There are two ways to look at it. One of them is sort of the standard position. And a vector like a comet has a head and a tail. And in standard position, the tail is always the origin, and the head is always a point 1, 2. And we call this vector 1, 2. The same notation. Pictorially, the vector 1, 2 starts at the origin and with the tail and goes to the point 1, 2. So here is the point 1, 2 at the head of the vector 1, 2. The advantage of vectors is there are other positions, other locations, you might say. And to do it, you simply give a different tail. So for example, if the tail is the point 1, 3, so 2, 3 rather. So if we take 2, 3 for the tail, so here is the tail, the point 2, 3. If we go 1 over and 2 up, 1 over and 2 up, we get a vector that is parallel to this one, has the same direction, but it no longer ends at 1, 2, it now ends at 3, 5. So this is again the vector 1, 2. So if the tail is 2, 3, the head is 3, 5, the vector is the vector 1, 2. It describes how to go from the tail to the head. So this is the idea of vectors. There's an association with vectors and points, but vector is a little more flexible than point, and this is what we'll be looking at. So that is section 1. What is a vector supposed to do? How do you denote them? And the second thing I wanted to talk about is how we will write vectors. So what I could call is notation. And so the first notation is as rows. All of this is sort of geometric. And again, let's be in R2. So the vector, these are vectors, or could be considered vectors in R2. It can be useful to write them as columns. 1, 2, column vectors. So these are the same vectors, but just simply written as columns. We'll do both. In fact, we'll do all of this stuff. And the third way we would write them, which I'll put up here, is for use in Mathematica for computations, in which case a vector is denoted as just a simple list. Similar to rows, but actually not quite. So in usage, these are just lists of numbers. So these are vectors. All of these are denoted with a little vector sign above a letter. So a name for the vector 1, 2 that I'm going to use is U, and that little vector sign above indicates that this is not just a point, but this is a vector quantity. So these are the notations that we'll use. Next, I think on my list is the arithmetic, basic operations. So the basic operations, and there are 2 of them. The first one is addition. Any 2 vectors can be added. And if you add 1, 2 to 3, 7, this is equal to the vector 4, 9. And you could add as columns, I mean, it's the same. So addition of vectors works like this. This is called component-wise. These are the components. You add the first components, you add the second components, and you get the result. And the second one will have addition of vectors. So any 2 vectors can be added. The other one is you can scale them. This is not like fish. Scale means make them bigger or smaller, but don't change direction. So scaling means you can take the vector 1, 2, and you can make it twice as long, so you can multiply by the number 2. And if you do this, you get 2, 4. So all of these are relatively clear and fairly straightforward operations. Scalar multiplication, scale any vector, vector addition. Scalar multiplication, vector addition. You do not multiply vectors. We'll have some other operations on vectors, but these are the two basic ones that we'll use. And each of these has a little geometry. So let's take a look at the basic ops we did. And now let's look at the geometry of these basic ops. So this is the geometry of arithmetic. For example, if we take the vector 1, 2, and we add it to the vector 2, 3, we should get the vector 3, 5. Let's see how this works. So we'll begin by putting 1, 2 in standard position, over 1, up 2. Over 1, up 2. So here is the vector 1, 2. We want to add to that the vector 2, 3. And in order to add 2, 3 to this geometrically, we will take the head of 1, 2, namely the point 1, 2, and we will add, and that will be the tail of 2, 3. So we begin at 1, 2, and we'll go 2 units in the x direction, 1, 2, and 3 units up. So this is the vector 2, 3, but with the head here and the tail here. And where did we end up? Well, we end up, the point we end up with is the point 3, 5. And so we end up with the vector 3, 5. So taking 1, 2 as a vector, adding 2, 3 to it, head to tail, ends up with the point 3, 5, ends up with this little geometry. So this is the geometry of addition. Let's look at the geometry of scaling. So let's take 1, 2 and scale by 3, in which case we should get 3, 6. Now notice that the rise over run is 2 for each of these vectors. So they determine the same slope, namely 2. So rise is 2, run is 1, over 1, up 2. Here is the vector 1, 2. And here is the vector 3, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. So it should be the exact same slope, but ending up at the point 3, 6. So scaling means, if you scale by 3, it means a vector that is exactly 3 times the length and has the exact same slope. Both of these are in standard position, but we want to think of a vector as going from one place to the other. So this green vector could be moved and you could go 3, 6 from any head to any tail. Okay, so this is the basic arithmetic of scaling or scalar multiplication. And that's sort of all there is to arithmetic other than linear combinations. So a linear combination refers to vectors. So this is a linear combination of given vectors. So I'm going to give you a few vectors and ask you to find a linear combination. So on the sheet, I think I gave you the famous 1, 2, and 3, 4. So here are the given vectors. Vector is a linear combination of these two. Means, so I'll call this U, is a linear combination, means there are numbers like 4 and -2 that you can scale these vectors by and then add up the result. So a linear combination is a scalar times the first plus a scalar times the second. So what would we get here? Scale this, you get 4, 8, and then minus 6, 8. So the result would be -2, 0. A linear combination of 1, 2, and 3, 4 is the vector -2, 0. So -2, 0 is a linear combination of the first two vectors of the given vectors. How do you know? 4 times the first minus 2 times the second gives you that vector. And any time you take a linear combination of these two vectors, it means you scale the first, you scale the second, and add them up. If your given set of vectors was larger, let's say we're given the vectors in 3 dimensions, 1, 0, 2, 2, 1, 1, and 3, 1, 3. If we're given those vectors, what would a linear combination look like? It would look like some number times the first plus some other number times the second, could be the same or different, plus some other number times the third. So a linear combination means you scale each one. You could scale by 0, and every time you scale by different numbers and add up, you get a linear combination. So in this case, you would get 1 minus 2 is -1, 0 minus 1 is -1, 2 minus 1 is 1. So -1, -1, 1 is a linear combination of these three because there are scalar numbers, in this case 1, -1, and 0, which when multiplied by the given vectors gives you -1, -1, 1. So these are linear combinations. Now, one other thing I wanted to point out here is that when we've been doing solutions to a system of equations, we begin with equations, and from that system of equations, we get a solution. And our solution has a number of forms. So for example, a form might be 3t plus s, s plus t, 4t minus s. Here we would have two free variables, s and t. And this is called geometric form. So the geometric form of the solution might be this. We could also have a list form. The book does this. In this case, x1 is 3t plus s, x2 is s plus t, and x3 is 4t minus s. Writing the solution as a list. We're going to be most interested in geometric form. I wrote geometric form here as a row, but you could also list it as a column. So this is written as a row, but I wanted to show you can also list it as a column. 3t plus s, s plus t, 4t minus s. So here is the geometric form, one of these two that we will be using. And with either one, this is what I wanted to show you. Let's work with the column one first. You can separate this out into the t part, 3t, t, 4t, plus the s part, s S minus S. If you use vector addition on these two, you get this, but we want to go the other way also. If you take the solution that looks like this, plane in three-dimensional space, you can separate it out into these two components, each one represented by a parametric variable. And now you can factor out the variable. So t times 314 plus s times 1, 1, minus 1. So you can write the solution, this particular solution, as a linear combination of this vector and this vector. And you can separate it out in row form as well in the same kind of way. This would be t times 314 plus s times 1, 1, minus 1. So we will be doing this separating out. Let's take one more look at things here. This time I'll begin writing things as a column. And we'll again get another solution. We'll again have it in geometric form. We might have s plus 2t plus 1, 3s minus 4t plus 2, and let's say 2s plus t plus 7. So our solution might actually look like this. We can do the same thing. The result is a little different. We'll write it as an s part plus a t part. So it'll be s times this vector plus t times this vector plus a constant part. And in this case, the constant part is 127. The t part is 2 minus 4, 1. And each one of those will be scaled by this t, so this t will multiply through like you see it here. And then you'll have an s part, s, 3s, 2s. When you factor out the s, you'll get 1, 3, 2. Now, any of our solutions can be written like this: a linear combination of these two vectors plus a constant vector. Linear combo plus constant. So with solving equations, we'll always be able to write it something like this in geometric form, and then we can transfer geometric form to talk about linear combinations plus a constant. So that's it. So check your book, make sure that you've got the right book. We're working on the homework problems to make sure everybody has correct homework problems. Have a good evening. Watch the US Open, but not too much. See you tomorrow in class.